Every EV on the road today runs on lithium. CATL just swapped it for salt. Same salt in your kitchen. 500 kilometers of range, 40 PHNTRM cheaper to build. Performs at -20 C without breaking a sweat. And it's already in mass production. Lithium didn't lose a battle, it lost the war. For the past decade, the global EV transition has been running on a foundation that was cracking beneath the surface. Lithium isn't rare in the way gold is rare, but extracting it at scale is a different story entirely. The process requires massive evaporation pools spread across thousands of acres in South America. It demands extraordinary volumes of fresh water in regions that barely have enough to drink. And it takes years of chemical processing before a single gram of battery-grade lithium is ready for a cell. Then there's the supply chain geography. The majority of lithium processing and battery cell manufacturing is concentrated in China. Western automakers, from General Motors to Volkswagen to BMW, have spent hundreds of billions building EV platforms, on top of a supply chain they do not control. That's not a business risk, that's a structural vulnerability. And cobalt, the other critical ingredient in high-energy lithium chemistries. 60% of global cobalt supply comes from the Democratic Republic of Congo, a region notorious for supply instability and human rights violations that haunt every ESG report a Western automaker has to publish. The entire industry knew this was a problem, but nobody had a credible alternative until CATL officially triggered mass production of the Na-extra sodium ion cell, capable of a verified 500 kilometers of real-world range. Not a prototype, not a press release. Mass production. Here's the uncomfortable truth that most EV coverage skips over. Sodium-ion batteries are not a new idea. Researchers have been experimenting with sodium chemistry since the 1970s, roughly the same era as early lithium research. So why did lithium win, and why did sodium get abandoned for nearly 50 years? The answer is geometry. Specifically, ionic geometry. A sodium ion has a radius of approximately 0.102 nanometers. A lithium ion sits at 0.076 nanometers. That difference sounds microscopic, because it is, but at the atomic scale, it's the difference between a key that fits a lock and one that destroys it. In a conventional lithium-ion battery, the anode is made of graphite, a crystalline carbon structure with tightly ordered interlayer spacing of about 0.335 nanometers. When you charge the battery, you're forcing ions into that lattice, in a process called intercalation. With lithium, the ions slip in cleanly. With sodium, the oversized ions force their way in, physically expanding the structure with every charge cycle. The lattice cracks, the electrode degrades. Energy density collapses to around 90 watt-hours per kilogram, barely enough to move a bicycle, let alone a 2-ton SUV. Every startup that tried to commercialize sodium-ion batteries in the 2000s and 2010s hit this exact wall. The chemistry was interesting on a whiteboard. In a real cell, under real charge cycles, it destroyed itself. The conventional wisdom became, sodium is fundamentally limited by physics. Move on. CATL didn't move on. They looked at the problem from a completely different angle and realized the issue was never sodium itself. The issue was graphite. If sodium couldn't play by graphite's rules, the solution was simple. Eliminate graphite entirely. What CATL built instead is called a hard carbon anode. And the difference between hard carbon and graphite is not incremental, it's architectural. Graphite is ordered, crystalline, precise. Hard carbon is the opposite, deliberately disordered, amorphous, full of irregular micropores and variable interlayer spacing. Instead of a tight crystalline lattice that sodium ions can't fit through, hard carbon behaves more like a three-dimensional molecular sponge. The sodium ions don't need to force themselves into a rigid structure. They simply flow into the open pore network, park themselves, and flow back out during discharge, without ever stressing the electrode walls. The volumetric expansion problem, effectively eliminated. The structural degradation cycle, broken. But solving the anode was only the first half of the engineering challenge. The cathode, the positive electrode that governs voltage and total energy capacity, needed an equally radical rethink. CATL abandoned traditional lithium metal oxides completely. Instead, the Na extra cathode uses advanced Prussian white analogues, combined with complex layered transition metal oxides. Prussian white is a crystalline framework, with naturally open ionic channels. It was practically designed for large ion chemistries like sodium. By stabilizing this cathode structure at the microscopic level, to prevent transition metal dissolution, a failure mode that plagued earlier sodium cathode research, CATL pushed gravimetric energy density to 160 watt-hours per kilogram on commercial cells. That number matters enormously. 160 watt/kg is directly competitive with first-generation LFP cells. The exact chemistry currently powering the standard range Tesla Model 3, the BYD Seagull, and millions of other EVs in global markets. And CATL has already confirmed their next generation Na extra iteration is validating at 200 EW/kg, which begins to challenge mid-tier NMC chemistries. Then comes the cold weather performance. And this is where the Na extra architecture doesn't just match lithium, it humiliates it. Sodium ions have a significantly lower desolvation energy than lithium ions. In practical terms, this means the electrochemical reaction remains highly active even at extreme temperatures. Na extra cells retain over 90 PHN/TRM of their usable capacity at -20 C. Temperatures where standard NMC batteries lose 30 to 40 PHN/TRM of their range and LFP cells can lose even more. Fast charging, which becomes dangerously slow in cold lithium cells due to the risk of lithium plating, remains viable with sodium chemistry at 10 PHN/TRM to 80 PHN/TRM in approximately 15 minutes. The thermal management implications are significant. Automakers can strip out heavy coolant loops, high-voltage PTC heaters, and complex heat pump architectures, reducing vehicle weight and freeing up packaging space that translates directly into range or cost savings. The engineering story is compelling. The economic story is where Western automakers should be genuinely alarmed. Sodium is the sixth most abundant element in Earth's crust. It's extracted from seawater, brine deposits, and salt mines on every continent. There is no supply bottleneck. There is no geopolitical choke point. There are no evaporation pools consuming fresh water in the Atacama Desert. The raw material cost curve for sodium starts at a fundamentally different baseline than lithium. And it doesn't get more expensive as demand scales. It gets cheaper. But the bill of material savings go deeper than just the active material. In a standard lithium-ion cell, the anode current collector must be made of copper, because lithium chemically alloys with aluminum at low voltage potentials, making aluminum foil unusable. Copper is dense, heavy, and expensive. Sodium doesn't alloy with aluminum at low potentials. That means CATL can use thin aluminum foil for both the anode and cathode current collectors. Eliminating copper from the cell architecture entirely, remove lithium, remove cobalt, remove nickel, remove copper, replace all of them with sodium, aluminum, and Prussian white derivatives. Current industrial cost analysis suggests Na extra cells are approaching 30 to 40 PHN/TRM lower cost per kilowatt, compared to base LFP cells. For a company manufacturing millions of battery packs per year, that cost delta isn't a competitive advantage, it's a weapon. CATL's deployment strategy amplifies this further through their AB pack integration system, a battery management architecture that physically combines sodium, ion and lithium, ion cells within the same structural pack housing. The software dynamically allocates load between the two chemistries in real time. Sodium cells handle high current demands like rapid acceleration, cold starts, and DC fast charging, while lithium cells serve as the deep energy reserve for steady highway cruising. The result is a hybrid pack that mathematically cancels out the weaknesses of both chemistries simultaneously. The 310-mile sodium ion cell is not a future product on a roadmap. It is in mass production today, and it will begin appearing in mid-size sedans and compact SUVs in global export markets within this model cycle. For automakers in Detroit, Stuttgart, and Tokyo who signed decade-long lithium supply contracts, who built gigafactories around lithium cell formats, who tied their electrification strategies to lithium chemistry. The timeline just compressed in a way that boardroom planning cycles weren't designed to handle. The Chinese domestic market has produced a battery architecture that is immune to lithium supply constraints, performs reliably at temperatures that paralyze conventional EV chemistry, and costs structurally less to manufacture at every level of the supply chain. The age of lithium dominance isn't fading gradually. It's being replaced methodically, commercially, and at scale. The rules of electric vehicle engineering have been rewritten. The only question now is how quickly the rest of the industry can respond.